Hi folks, welcome back to Physics with Captain Rod here. Let's see, I'm making this video to help demonstrate how to apply momentum methods. So let's see, a person kicks this ball, it hits the ground 15 meters away, find the impulse that the foot put onto the ball. Okay, so let's go ahead and start with, or chat about the impulse part of this. So the ball, before impact from the foot, all right, the ball's just sitting here. All right, I'm going to call this picture 1. There is no momentum because the ball's not moving yet. All right. Now you'll notice that after impact we have a velocity vector here, 30 degrees with the horizontal. So the impulse must have had both horizontal and vertical components to it. So in our impulse diagram, we can either put the F delta t like this, an Fx delta t, and an Fy delta t, right? Or we can put a single force vector and tack a delta t at a 30-degree angle. I'm going to go ahead and just leave it like this. It'll be, I'm sure it'll work out just fine, but either one is just fine. And then our picture 2 here, the ball has a momentum up and to the right, so we'll label that vector, let's see, how about mv2 at an angle of 30 degrees. Now you'll notice I called this like picture 1, 2, and you might be wondering, why is this not picture 2? Well, your impulse picture needs to include all impulses between our initial and final state here, if you will. So I think what makes the most sense here is we'll call this one picture 1, this one picture 2, and then the middle picture I usually label 1 to 2 because it's everything that happens between those two states. Okay, now the question is to find the impulse on the ball. So basically it's to find that Fx and Fy that I drew, and then we'll tack delta t's on. Now what we're going to have to do is we're going to have to deal with the projectile part of this problem. So the ball starts with some sort of initial velocity vector. Now I label that v1 here at an angle of 30 degrees. And it hits the ground 15, I think, meters away. So this is a projectile problem, so we'll start by breaking the velocity vector down into horizontal and vertical components. All right, so that one right there would be v1 cosine 30 degrees, the vertical component v1 sine 30 degrees. Then we analyze the motion independently. In the x direction, we expect an acceleration of 0, ignoring air drag. And keep in mind that this is dv dt. So that means that's going to integrate to v equals a constant, which is going to be v1 cosine 30 degrees. And keep in mind this is dx dt. This now integrates to v1 cosine 30t plus another constant. But if we put our coordinate system here at t equals 0, x is 0. So we get v1 cosine 30t is equal to x. Okay. Now we look at the y direction, where we expect the acceleration to be minus g. And you could also just put g here, okay? And it might seem a little weird, why can we put either? Well, in my formulation here, the minus sign already takes the direction into account. So later on, numerically, you would put g equals positive 9.8 meter per second per second. If you put acceleration equals plus g here, then later on, numerically, you put in minus 9.8 meter per second per second. But anyway, moving on, keep in mind that this is dv dt. Now this is dv in the y direction times dt. This now integrates to v equals minus gt plus a constant. I guess, let's see, constant-wise, I'm up to constant 3 here. Now, at t equals 0, this is our initial velocity. So Vy equals minus gt plus V1 sine 30. Okay, now keep in mind this is equal to dy dt. So that is going to integrate to y equals minus 1/2 gt squared plus V1 sine 30 plus, I'll put C4. Putting a coordinate system origin here knocks that over. Okay, so now the rest of this problem, all right, is basically numerical. And I don't have a calculator handy. I'll let you folks work this out. But when the ball hits the ground 15 meters away, what you can now do is you can put a 15 right here. Okay. Solve this for t, and it's going to read 15 meters over V1 cosine 30. I guess also you could just leave it as x, okay? Then this goes here and here. I forgot a t on there. Whoops, my bad. Sorry about that when I integrated. Okay, and the following equation out of that, you'll be able to solve that for V1. And now, let's see, and I'm reading the problem. Find the impulse that the foot is put onto the ground here. Well, when we look at our momentum equation, oh, and I see, I haven't really had enough coffee here, sorry. This one was for the projectile problem, okay? Now, when we go back to our momentum diagram, that's this velocity right here. Because remember, these 1s and 2s, we're talking about the impacts. And basically, you'll notice that when you look at our picture, we have 0 momentum plus this equals this. So Fx delta t, that's the x component of our impulse, is equal to mv2 cosine 30. So once you have v2, you can get a number out of this. And remember, that represents the x direction. Now when you look at the picture for the y direction, you've got 0 plus Fy delta t equals mv2 sine 30. And again, once you have v2, you can get a number out of this. And there is your impulse, right? Basically, these numbers right here is your impulse. We would have it in component form. So let's write it like this. So your impulse is going to equal, I'm just going to call it Ix in the I direction, and this is your impulse in the x direction, plus your impulse in the y direction times j to give it a direction. That's this number. You could then Pythag it and to find a magnitude, and the angle's basically already there. So I was making this video to help kind of demonstrate how to use impulse momentum diagrams, and I guess this one had a little projectile problem to boot. I hope that this helps. Have a great day.